readability of mathematics story problems. So we have gone through this kind of cycle, not the right paper part of it, but the rest of it. So I'm just going to, in my presentation, just kind of go from one stage of the cycle to the next. So that didn't end up being linear for us. So we were developing an idea. We had conducted several correlational studies about how readability factors, such as the number of sentences and the use of pronouns, were related to performance on mathematics story problems, focusing mainly on algebra story problems. We were using text mining tools like Cometrics to kind of data mine existing banks of mathematics story problems and students' performance and then associate the two. We also used the NAEP and the TIMS. And these were just problems that happened to vary on these readability measures. They also varied on their mathematical characteristics, so we were trying to control for the mathematical characteristics and just look at the effect of readability in existing data sets. And from this, we were able to narrow a list of promising readability factors that might be associated with performance that we wanted to test in assessments experimentally, where we could have control over different versions of problems that were mathematically identical but that varied on factors like the number of sentences, overlap, pronouns, topic, concreteness, and hypernymy. And we wanted to conduct what's called the difficulty factors assessment, where we systematically vary readability factors for mathematically matched problems. But one thing that we kind of were concerned about from the start that I'm going to come back to at the end is that effect sizes in this domain are generally very small. So large sample sizes are needed to be able to detect the effect of putting one pronoun versus another in a story problem. So the first thing we did was we created a problem set. So for each of our factors, we would create algebra story problems that on that factor were not readable, moderately readable, or very readable, based on some things we found in our prior work. So this is just an example for a number of sentences. In the 4-sentence problem, there's a sentence that's purely context at the beginning that gives no mathematical information, and a sentence for the slope, and a sentence for the intercept. The moderate readability, that context sentence is gone, and the very readable, the slope and intercept are combined into a single sentence, so we only have 2 total sentences. And similarly for pronouns, these were more just hypotheses how it would pan out in terms of what pronouns are not readable versus very readable. From our previous work, we felt that no pronouns would probably be the least readable, whereas third-person pronouns had been coming out as being very readable in our prior analyses of existing data sets. So we programmed all of these problems into assessments. We had a bunch of other factors that I mentioned before, like concreteness and hypernymy, that also had their problem versions. We wrote 2 different problems with 3 problem versions for each readability factor of interest. So for number of sentences, we had a 2, a 3, and a 4, and then another problem that was also a 2, a 3, and a 4. Just in case there's something weird about one problem, we would have another problem to kind of fall back on. This is what our problem set looked like. So there's the pronoun, the first pronoun problem is the first hypernymy, the first number of sentences, the first overlap, the first topic, and then the second of each of those factors.
That's random.
Yes.
So the kids went through, they had to do all of those.
Right.
So
they
the
had
kids
to
did all of those, but each one has a choose, you can see that it has a choose condition.
Yeah, so there was a choose condition set on each. So of the 3 different versions of each problem, it would randomly choose one version for them to get. So it wasn't like a participant was just assigned to a very readable condition and stayed in that condition. It was varied for every single problem that they solved so that we could do a stronger within subjects design rather than a between subjects design and kind of maximize our sample size. So each student had 12 problems because there were 6 factors and we had 2 different problem stories per factor. We used the random order to vary the order of the problems. So if they learned from one problem consistently, it wouldn't affect later problems. And then we tagged it with a Common Core standard for 8th grade, construct a function to model a linear relationship between 2 quantities. This was so the teachers would be able to find the problem set and know what they could use it for immediately. So the next step was students using the problem set. We posted an advertisement for students, and delighted to say that we currently have about 100 students per problem version, which was a lot more than we expected. However, we were surprised to see only 15% are actually in 8th grade, given that it's an 8th grade Common Core standard, and that our advertisement said, hey, 8th grade teachers, look what we have for you. There were a lot of people who did this study who were not in 8th grade. So around 50%, a little bit under, are in grades 7 through 9, which is what we could probably reasonably use for this study. So our next step was to analyze the data. As Christina showed you, we received the data in a Google spreadsheet, and there were a lot of useful information in the spreadsheet, whether they got the problem correct, what they actually typed, so we could track what their mistake was if they got it wrong, using what they typed. What their prior percent correct was is kind of our control for mathematics achievement, so very rough proxy.
And that's prior on, if that child has done anything in assessments ever, that's their prior for everything they've ever done. So you can kind of chunk that by class. Did you guys look at that prior? Did you just sort by that prior? Or did you sort by, within each class, by the prior?
Okay, so it'll vary by class too.
Right? Because there's some teachers who only give easy stuff. And there's some teachers that give hard things. And so it's really from within your class where that number makes any sense.
But,
Yeah.
This is actually, so what do I do on this project? I think about this sort of stuff. And so, among other things, I want to make it easy for you to actually do a hierarchical learner modeling. So we actually give you teacher IDs as well as school IDs. So we can do that. But also, we're actually working on actually doing other ways of actually ranking, doing a percentile rank for each kid nested within a class. And that way, because different teachers are assigning different stuff, so that element will continue to get more
Yeah, so you
robust.
might see a new column someday, and there will be a new item. You'll see the column, and then you'll go to the glossary and say, what the heck is this new column? Because that's all, we're always coming up with new things to put onto this data dump. And Neil's trying to make the data dump smarter. So it's this combo that's sort of growing. You've probably seen it change over the last, you know.
It also gives whether they asked for a hint, although our hint was just answered.
Right.
In this case, we didn't program in more advanced hints, attempts, how much time they spent, gender, grade level, and then another column for which of the problem versions they received, so that we could say whether it was not readable or very readable.
Do they really spend 8,000 hours? I should say it's in milliseconds. So times.
Do you capture ethnicity at all?
No, and the gender is only guessed.
Oh. Yes.
You can look at the glossary was here. Well, I can't.
So we initially analyzed our data, and this is just an example for the two that I showed you before. For number of sentences, we saw it's actually that jump from 2 sentences to 3 sentences that causes correctness to drop. The contextual sentence at the beginning actually doesn't do very much. It's just combined the slope and intercept into a single sentence versus breaking them up into 2 sentences that seems to be most important for number of sentences. For pronouns, the effects are smaller, which fits with what we saw in our prior work, and didn't quite go in the direction that we expected. Second person pronouns were actually the most readable, according to this, with no pronouns being moderate and third person pronouns being hardest. However, our problem right now is that the standard errors are too high to detect most of our effects. So we can definitely detect the number of sentences one. That one's big enough that the variability in our data set is large, but we can still see that the 2 versus 3 sentences is significantly different. Most of our other effects are too subtle to be detected with our current sample size. And this is partially because the students are so variable in their grade level, it created a lot of variance in their performance on these problems. We also had some unexpected results with our hypernymy and topic comparisons, which gave us the realization that we hadn't perfectly matched word count across conditions. So if you're comparing different versions of problems, it's really important that they have the exact same number of words, otherwise you can't really say if it's your condition that caused the difference or if it's word count that caused the difference. So we had to come back and recreate our problem set to fix the word count issues in some of our versions. And we relaunched the set after we did.